Hello everyone, today we're going to start reading about magnets and magnetism, so you can follow along. This is chapter 2, section 1 in your textbook, and it begins on page 38. You've probably seen magnets like the ones at right and below stuck to a refrigerator door. These magnets have been used to hold up notes or pictures, or might have been used just for decoration. If you've ever played with magnets, you know that they stick to each other and to some types of metals. You also know that magnets can stick to objects without directly touching them, like when it is used to hold a piece of paper to a refrigerator door. How do magnets work? Read on to find out. Properties of magnets. More than 2,000 years ago, the Greeks discovered a mineral that attracted objects containing iron. Because this mineral was found in a part of Turkey called Magnesia, the Greeks called it magnetite. Today, any material that attracts iron or materials containing iron is called a magnet. All magnets have certain properties. For example, all magnets have two poles, exert forces, and are surrounded by a magnetic field. Magnetic poles. The magnetic effects of a magnet are not evenly distributed throughout the magnet. For example, if you dip a bar magnet into a box of paper clips, you'll find that most of the paper clips stick to the ends of the bar, as shown in figure 1. As you see this, the magnetic effects are strongest near the ends of the bar magnet. The parts of a magnet where the magnetic effects are strongest are called poles. So the magnetic force is strongest here and here. North and south. If you attach a magnet to a string so that the magnet is free to rotate, you will see that one end of the magnet always ends up pointing to the north, as shown in figure 2. The pole of the magnet that points to the north is called the magnet's north pole. The opposite end of the magnet points to the south and is therefore called the magnet's south pole. Magnetic poles are always in pairs. You will never find a magnet with only one north pole or a south pole. Magnetic forces. When you bring two magnets close together, the magnets exert a force that can either push the magnets apart or pull them together. This force of repulsion or attraction between the poles of a magnet is called the magnetic force. The magnetic force between a pair of magnets depends on how the poles of the magnets line up, as shown in figure 3. As you can see, magnetic poles are similar to electric charges, in that like poles repel and opposite poles attract. So two north poles would repel, two south poles would repel, north and south would come together. Magnetic fields. A magnetic field exists in the region around a magnet in which the magnetic forces can act. The shape of a magnetic field can be shown with the lines drawn from the north pole of a magnet to the south pole, as shown in figure 4. These lines map the strength of the magnetic force and are called magnetic field lines. The closer the field lines are, the stronger the magnetic field. Magnetic field lines around a magnet are closest together at the poles, showing that the magnetic force is the strongest at the poles. Field lines are closest together here and here, therefore the magnetic force will be the strongest there. What makes materials magnetic? Some materials are magnetic and some are not. For example, a magnet can pick up objects such as paper clips and iron nails, but it cannot pick up things like paper, plastic, pennies, or aluminum foil. What causes the difference? Whether a material is magnetic depends on what atoms are in the material. All matter is composed of atoms. In the atoms, electrons are negatively charged particles that move around the nucleus. Moving electrons produce magnetic fields that can give an atom a north and south pole. In most materials, such as copper and aluminum, the magnetic fields of the individual atoms cancel each other out, so the materials are not magnetic. However, in materials like iron, nickel, and cobalt, the atoms group together in tiny regions called domains. The atoms in a domain are arranged so that the north and south poles of the atoms line up and create a strong magnetic field. Domains are like tiny magnets of different sizes within an object. Figure 5 on the next page shows how domains affect the magnetic properties of an object. So figure 5 shows that if the domains are randomly placed like this, south is over here, now south is pointing this way and down and right, this object is not going to be magnetic. However, this object, see how the south poles here are aligned? All the souths are pointing down except for this one. This object is going to be magnetic. The more domains that are lined up, the stronger it is. So if we flipped this one around so south was pointing down, the magnet would be stronger. Losing alignment. The domains of a magnet may not always stay aligned. Dropping a magnet or striking it too hard can jostle the domains of the alignment, causing the magnet to lose its magnetic properties. Increasing the temperature of a magnet can also demagnetize it. At higher temperatures, atoms in the magnet vibrate faster and lose their alignment within the domains. Making magnets. A magnet can be made from an unmagnetized object made of iron, cobalt, or nickel by aligning the domains in the object. For example, you can magnetize an iron nail if you rub it in one direction with one pole of a magnet. The magnetic field of a magnet will cause the domains in the nail to rotate and align with the domains in the magnet. As more domains become aligned, the overall magnetic field of the nail will strengthen, and the nail will become a magnet, as shown in Figure 6. The process of making a magnet also explains how a magnet can pick up an unmagnetized object, such as a paperclip. When you hold a magnet close to a paperclip, the magnetic field of the magnet causes the domains in the paperclip to align slightly, creating a temporary magnet. The domains align such that the north pole of the paperclip points towards the south pole of the magnet. The paperclip is therefore attracted to the magnet. The domains of the paperclip return to a random arrangement after the magnet is removed. Half a magnet. What do you think would happen if you cut a magnet in half? You might predict that you would end up with one north pole and one south pole, but that's not what happens. When you cut a magnet in half, you end up with two poles, or two magnets, each with its own north pole and south pole, as shown in Figure 7. Each domain within a magnet is like a tiny magnet with a north and south pole, so even the smallest pieces of magnets have two poles. We're going to stop here. You can listen to the next audio file for types of magnets.